Good morning, students. Today we start with our new topic, it's set theory. So, this lecture we will first introduce the set theory. Before we do counting, so we'll see the basic definitions, operations on set, and set identities. So, defining the sets. So, set is an ordered collection of a distinct object. We can say set is a collection of a distinct object of a same type. So object, what is this object? Object in a set are called the elements or members of a set S. So we say set S contains its element. So we can define a set by directly the listing all its elements. For example, S is equal to, you have to write down in a curly bracket. It's 2, 3, 5, 7, 11, 13, 17, 19. So this 2, 3, 5, 7, these are the elements, and whatever set we have considered, right? So for that set, whatever elements are, you have to show in a curly bracket. Second, that is S equal to A, B, C, D. So these are the set. So listing all its elements. Second, after we define a set is a single mathematical object and it can be an element of another set. So, for example, like this S is equal to. So, this is also one kind of a set. So, define a set by the properties. So, it is inconvenient or sometimes impossible. Define a set by listing all its elements. Alternately, we can define by a set by describing properties that its elements should satisfy. We use the notation. So these are the built-in notations. So X in curly bracket, X belongs to A. Right? So whatever this notation define. So what is this definition? Define the set as a set of elements X in A such that X satisfies the property P. So same here again. Another example, X is an element such that X is a prime number and X is less than 1000. So another example, X is element, or X is a set of elements such that X is a real number and minus 2 is less than X. X is less than 4. So examples of sets. So well-known sets are set of all real numbers, R, set of all complex numbers, C, set of all integers, Z, set of all positive integers, Z plus. So these are the different well-known sets. So empty set always derive this 5 or in empty curly brackets. There is a set with no elements. So membership order number of occurrences are not important in a set. So generally, whatever we set we represent. In a set, one elements occur one time in a set. If there are multiple times occur that element, always we consider that as a single element in a set. The most basic question in set theory is whether an element is in a set. Right? If element is in a set, then how we represent that? If element is not in a set, then how we represent that? So whenever any element belongs to that set, for example, X is an element of A. So how we represent? So we represent like this. So this X is belongs to A, right? And X is an element of A. X is in a, and X is not the element of A. X is not belongs to. X is not in a A. So cardinality of a set. So what is this cardinality? Cardinality is nothing but the number of elements uh, contained in a set. So always denoted in this mod of S. So this mod of S is nothing but the cardinality of a S. That number of elements occurred or number of elements present in that set. So that's if S is equal to. So these are the different elements. S is a set and containing 2, 3, 5, 7, 11, 13, 17, and 19. So what is this cardinality of this S? The number of elements. So how many elements are there? There is 1, 2, 3, 4, 5, 6, 7, and 8. So then S is equal to this cardinality of S is equal to 8. Same here, if S is equal to, so there are the different elements, right? So how many elements are there? 1, 2, 3, and 4. So this cardinality of S is equal to 4. Same here, cardinality is S is equal to 6. So there are the different subsets are 1, 2, 3, 4, 5, 6. These subsets are the elements of this set S. So what is the cardinality of S? This S is equal to 6. Then subset. So what is the subset? Suppose there are two sets A and B, right? So this A is a subset of B. So we denoted by this symbol. This A is a subset of B. If every element of A is also an element of B, then this A is a subset of B. So same here. So this is your outer circle is B, right? And inner circle is A. So whatever all the elements of this set A, right, R belongs to this B. Is whatever all the elements of A, that elements of B also, right? Means here A is a subset of a B. A is a subset of a B. So if A is equal to 4, 8, 12, 16, and set B equal to 2, 4, 6, 8, 12, 14, 16, then A is a subset of B. So here, see here, these elements of A, 4, 8, 12, 16. Right? There are four elements. These four elements are belongs to this set B. There is 2, there is 4. 4 is also present in B. 8 also belongs to this B. 12 also belongs to this B. 16 also belongs to this B. So whatever all the elements, these four elements, 4, 8, 12, 16, are belongs to this B. So this A is a subset of B. But this B is not a subset of A, right? Because all the elements of B is not belongs to A. So there is 2, 6, 10, right? These elements are not belongs to this A. So B is not subset of A, but A is a subset of B. proper subset. So given two sets A and B, we say that A is a proper subset of B is denoted by this symbol. That is A is a proper subset of B if every element of A is an element of B, but there is an element in B that is not contained in A. Means there are some elements of B that are not belongs to A. And we can say that A is a proper subset of B. There is fact. If A is a proper subset of B, then cardinality of A is less than cardinality of B. So for a given two sets A and B, we say that A is equal to B if that is A is a subset of B and B is a subset of A. So when we say that these two sets are equal, meaning is when we say that two sets are equal, if the both elements of the two sets, suppose that's A and B are two sets, so both elements of two sets are same, then we can say that these two sets are equal. That is, A is a subset of B and B is a subset of. If A is equal to B, then cardinality of A is equal to cardinality of B. Cardinality of A is equal to cardinality of B. So okay, we stop here. Next lecture we'll see next time.